Well, happy Wednesday to all. Last class, we left off talking about the Colorado River and the influence of the Colorado River in determining mitigating drought and determining water resources in the desert southwest part of the country. I'm not going to go through this all again, but just to get everyone, remind everyone up to speed. This basically drains the western part of the Rockies all the way from central Wyoming down to southern New Mexico and Arizona. All the water in this region basically flows out of the Colorado River. And the general story we were talking about at the end of the class on Monday was the fact that over the course of the last century, a large number of dams, hydroelectric power generating stations, and aqueducts are built to basically utilize this water resource in order to effectively irrigate much of the desert Southwest. So with major implications to LA, San Diego, Phoenix area, of basically all the Western Four Corners area, Nevada and California, in part, Southern California receive a significant amount of water from the Colorado River. So again, just to catch everybody up, to review here, this is one of the most controlled, controversial, and highly litigated river systems in the world. But as I mentioned in the class on Monday, is incredibly important for actually survival of agriculture in the United States. This is the largest food producing region in the country. And the 29 dams, hydroelectric power generating stations, and aqueducts that deliver that water, literally drive one of the two main breadbaskets of our country. But really, right at the point where we left off was talking about the fact that in 1922, the Colorado River Compact was signed, and that basically parceled out the water in the river between the upper and lower basins at the time, according to the size of the populations of various states. And it wasn't until the middle of World War II, actually 1944, that a U.S.-Mexico treaty allocated some of the water to Mexico. At that point in time, what the main reason that was done is that its population in the Southwest started to increase. Mexico was no longer actually seeing a trickle of water through Colorado, and a treaty was given to partition out according to the population at that time. So Mexico gets about 9.1% of the Colorado River water. The United States 90.9, and then that, of course, that was, as I mentioned again, separated out according to the population, which includes some major cities and agriculture areas, including Los Angeles in the area. So moving forward, the key here is that dams on the river and the tributaries. I won't test you on this specifically by any means, but this gives you a sense. There's dams that dam the Colorado River and control water management in this region all the way back up into Wyoming, into the western foothills of the Rockies, or into the western Rockies themselves, and actually provide water to many parts of the drainage basin. You notice there's some areas grayed out here. I'll come back to this in a second. But the areas that are grayed out are dominantly Native American reservations. You'll note, you're thinking about issues like social justice issues of water. They were not included in this percentage of water distribution, and as a result, have been largely off of the municipal water supplies from the Colorado River throughout the time. So this decision, while it clearly has provided water, allowed expansions of populations in the Southwest, from a sustainability perspective, it should raise a lot of questions. And most of those questions are around the idea of having a greater number of people, pretty rapidly increasing populations, increasing more quickly, quite frankly, than the U.S. population as a whole, moving to that region. As a result, the critical nature of the water stress in this area stricken by drought, historically and climatologically, in fact, raises a lot of questions. In fact, as I mentioned a few classes ago, in the last 20 years, in midst of this major drought in the Southwest, the populations in those areas have been increasing higher than the national average. In fact, the U.S. populations are redistributing to these areas, not moving out of them. So we're clearly in a situation where sort of the natural order of humans living where resources are sustainable is kind of out of whack. In addition to just the general lack of water, there are some other important environmental impacts of the Colorado River decision that I want to make you aware of and discuss a little bit. So one of the key ones is that historically the river transported 80 to 90 million tons of sediment to the Gulf of California every year. As we talked about a few lectures back, in terms of nutrient delivery to these areas, for starters, it has slowed the amount of primary productivity in the region. and minimize the amount of algal and photosynthetic growth in the area, which has implications for global carbon dioxide levels, of course. It's also actually, although there's not many concerns of cyclones in the area, it's also made the coastlines in those areas, rather than seeing a net growth of sediments in those areas and deposition, it's actually seen coastal erosion in those areas. But more importantly, probably to the perspective of the region itself, is that while there's the benefit of water, there's actually a reduction in wetlands and major ecological systems in the area. So these nutrients, along with the water that transports these sediments, were played major roles in nourishing wetlands, riparian areas along the river's natural course. That today, those nutrients are no longer being delivered, and as a result, in many cases, water is no longer being delivered. As a result, there's been a rapid decrease in wetlands and riparian zones across the entirety of the desert Southwest. In fact, this has major implications not just for local ecology, but also these are, if you think about I'll just go back quickly. If you look at the map of the United States here, these are major areas for transport of migratory birds and things like that in the region. So the whole western half of the country sort of funnels down to the western side of the Rockies there along the Cordillera. And in fact, that's no longer, there's still wetlands and riparian zones, but they've been significantly reduced, and many of them have been lost, which has a lot of implications for migratory birds and things like that. The other side effect, of course, is that the majority of material is actually deposited in the major dams. So, for example, the biggest are in the Lake Powell and Lake Mead regions. That's where up in the Rockies, there's enough topography to carry the sediments out. Once you get into the sort of plateau region, as you go towards the desert Southwest, there's less changes in topography, and as a result, Lake Powell and Lake Mead are actually filling really rapidly with sediments. That changes things about the water quality, but importantly, although it's not going to affect it on our lifetimes, it's estimated that we're going to be, within a few hundred years, 300 to 700 years, Lake Powell will fill entirely with sediments, and quite frankly, the cost of dredging something like this is just borderline unfathomable. So it's a problem we're not going to be able to really correct unless we find other ways to deposit sediments, which are just going to move the problem elsewhere. Another big issue with this region, with this planet in this region, is just like we talked about with California reservoirs. Of course, the reservoirs are essential. They're needed to provide water to the growing populations in the area. We certainly want to make sure that they have sustainable drinking water supplies. But the realization is that most of the water is still used for irrigation, for agriculture in California region, in the Imperial Valley. And just like California's other reservoirs, evaporation from the reservoirs in this part of the country is pretty profound. In fact, it's now a major problem along the Colorado River Basin, with estimates suggesting that 15% or more is lost through evaporation. Evaporation is so important that within sort of the microcosm or microclimates around some of the reservoirs, many of the sort of cloud and precipitation events are actually reservoir water that evaporates and deposited, sort of near the region. So all these, of course, impact the merits of trying to do this major, dam and irrigation processes. It reduces the amount of the resources that are present for people to utilize in the area. And of course, it's always this question of it not being distributed equally, specifically given the fact that, since 1922, the population distributions have changed quite dramatically in the area. Areas like Arizona and Phoenix, which have increased rapidly in the last 50 years, for example, are actually underserved and have, places like Phoenix and Tucson have, pretty serious, water shortages. So are there solutions? I'm going to say this as an example of something they're doing. I'm not actually advocating for this solution. In fact, I think it's a little bit silly, but there are efforts to try to reduce the amount of evaporation occurring in the reservoirs. You can imagine in these incredibly large lakes just how challenging it is to do something like that. You're not going to build a roof over it. You're not going to control the climate. So one of the techniques people are doing is actually trying to add these sort of plastic floating balls on top of reservoirs. This has been done particularly in Southern California. And if you think this is a ecologically friendly or a sustainable solution, I beg you to reconsider. But basically, the goal here is to put these balls in the reservoirs. I'm going to show you a picture here, take a brief aside, but notice just how far below the spillway the reservoir actually is in this region. So you can see that, first of all, the reservoirs, not just because of evaporation, but because of drought, are stressed. And the goal is that basically by introducing these balls, you can reduce the surface area of the water where evaporation can occur. Basically, evaporation is a function of temperature and surface area contact with air. So if you fill up a lot of that space with these balls, that can minimize some evaporation. Pretty clearly they'll absorb the heat rather than letting that heat be transferred to the water. And basically, from the perspective, at least from my perspective, it might reduce the evaporation, but of course it's going to create a whole nother cavalcade of problems. For example, things like PFAS and PFOS and microplastics getting into the water supplies just creates another string of problems. So this has been a solution that's got a lot of attention. It's been deployed in certain areas. This is actually in Southern California, a reservoir where a full truck of these things were unloaded and rolled into the reservoir to help reduce evaporation. And I'll highlight it as an example of a thought process on sustainability, at least from my perspective. I'm sorry to interject my opinion here, but the reality is that it does reduce evaporation locally, and it provides a mechanism to mitigate water loss. But as you can imagine, there are issues with getting too hot where they could break or crack. Many of them actually will split in half, and more importantly, they actually degrade, and they thought they only last about 10 years. And then, additionally, these create some other issues with people trying to use it for recreational purposes. One of the long-standing themes in conservation is finding a consumer to basically utilize an area. In animal management, for deer herds, we sell hunting license and have people who want to be able to hunt, so they manage and control the herd, and they buy land that preserves areas for animals to thrive. You can all have your own value judgments on that, but in reservoirs, one of the thoughts in order to generate revenue to minimize or develop technologies to minimize these things is to have recreational activities in reservoirs, so people boating and fishing and things like that. So it's unclear how these will affect those sort of aspects as well. So I have a question now. I mean, can anyone, before we move on, can anyone think of other ways to manage the water in the reservoirs, or any civilization saving ideas in the Southwest that can be thought of that can minimize the amount of water that we lost from a reservoir? It's okay not to have any trillion-dollar ideas or billion-dollar ideas early on a Wednesday morning, but it's a solution question that really begs to be answered. I'll give it a few seconds to see if anybody has any off-the-cuff incredible ideas, but otherwise I'll tell you some of the other strategies that are being developed. So one of the other strategies that are being developed in this region, I'll just go back here a little bit, is that rather than damming things into reservoirs, there's actually an effort now to do something called MAR, or Managed Aquifer Recharge. The goal being that rather than developing big reservoir lakes, we're actually going to divert the water in certain times of the year where there's great amount of flow, and actually do injection into the subsurface. So put the water into the ground, allow the groundwater levels to sort of increase or in many cases recharge in areas that have been overutilized, where that's still possible at least, and that will protect it from evaporation, and often in many cases over time purifies the water and increases the nutrient content of the water. So there's not a really great solution here. One that's being tried particularly in Southern California and around Phoenix area, Albuquerque, near the major cities, is to actually store water in the ground, trying to find, as we'll get to in the next series of lectures, trying to find locations where water can be easily recharged into the ground, where it can be accessed by pumping, where even though you might have a cost of doing that pumping, it's more economic because you're not losing so much of the resource. So that's a direction people are going in. Beyond that, it's quite challenging actually. You're talking about very large sums of water. Another issue that comes up with managed aquifer recharge is that, well, what does that mean for the amount of water people can use? Can people, can that be regulated to monitor the water usage in that area? So bottom line is, still in 2020, almost 98 years after the compact was signed, there's still a very uncertain future for the Colorado River. One of the biggest issues facing the future of the Colorado is the fact that the River Compact was actually drafted in the 1920s, and at the time it was using the best science that was available, science and engineering that was available, and actually the compact, as well as the distribution according to population, was based on 30 years of stream flow data from the Colorado and the region. Excuse me. But what was basically resulted at the time is that the results suggest an average flow of 17.5 million acres of feet acres past leased area. Now we'll talk more about what a acre feet or foot acres are later, but basically at the time it was based upon populations, and it was based upon very exacting measurements of water flow to distribute how much water would be in the region. Unfortunately, a more recent investigation, we've actually been able to understand paleoclimate, understand the water, the wetness in the region, is that it just so happens that the 1890s through 1920s were amount to basically three wettest decades in the past 500 to 1200 years in the region. So effectively, we set the threshold for how much water we use at the absolute high for the amount of water flowing past Lee's Ferry in the region, and as a result, most of the not only has the population changed over the 100 years since we set the regulations, but actually the amount of water that's been flowing through the region off the Colorado during the entire time is actually realistically less than what we thought it was when we set the regulations. Just back here, sorry, the slide's out of place, but I just wanted to highlight that there are many populations, particularly Navajo and other Native American tribal reservations there that didn't actually get any water partitioned to them at all. So, the reality is that the natural flow on average over the last 100 years is actually, about 25% less than we thought. So in addition to the fact that population is increasing, the amount of water is decreasing, and the population, of course, changing, in a non-uniform manner, we have the issue about the fact that there just simply isn't as much water in the area as we expected. So the punchline to all this is that the net result is that more water has been allocated to users than actually flows to the river. That's an annual problem in most years, particularly in the dry years, like we talked about for California. It can become an incredibly risky proposition where there's really no good solution to how to actually balance the water budget. So, for perspective, you've seen this if you've traveled to this area recently. At the time the Lake Mead was built, the levels increased. We're more or less, sort of steady and below storage capacity. Actually, towards the end of the last century, there was a series of wet years, and population hadn't really started to take off there yet, although California had been increasing all the while, and it was actually close to the storage capacity of Lake Mead. However, since the drought from 1998 on, you have both population increases and the drought, in the region, particularly California and the Southwest, and as a result, we've seen the lake levels drop, and they're continuing to drop. If you were to actually head out to Lake Mead, you'll see this sort of looks like a white rock around the entire thing. It's not white rock; it's actually mineral precipitate salts, carbonate minerals, and they actually are just it's literally the nutrients that were in the water. When the water dried out, the nutrients created a bathtub rim around the Lake Mead of dried up minerals in the area, and that's a thing that continues to draw down still to this day. So the goal here is to basically, the best case scenario here realistically is to use the lakes as reservoirs, even recognize we're going to lose 15% of the water each year, and use them to store up enough water so that we can sort of distribute the water as best needed. So generally speaking, if that works, to pond it up and use it when it's most in demand, but it also creates some issues with what to do for water supplies in times, otherwise. And as we highlighted before, and we'll talk about more in the remaining part of the lecture today, mostly this is basically met with utilization of groundwater, which is not which is renewable, but is not renewable in the time frames that we are really interested in this area. So it's a major water crisis that will continue to be an issue throughout all of our lifetimes. This will give you a perspective on Lake Powell. The Lake Powell's, of course, located in a very arid environment. Water level varies considerably according to the rain events of the season. There can be pretty rapid flash floods, and there can be great refill at certain times. But in reality, when water is being consumed at pretty high rates, it can be drawn down continuously. Notice that the addition of Lake Powell actually causes some ponding up, or damming up of the water in the area, and actually leads to localized flooding and some lakes even backstream, or upstream rather. So Lake Powell is usually considered to be the best barometer of the water conditions. The monitoring the levels of Lake Powell are pretty much reported daily, and give you a sense of the of the integrated drought in the area, recognizing that when there's not enough water for use in local reservoirs or whatnot, the Lake Powell's drain to increase water downstream. Just to highlight, as recently as the mid 90s, the reservoir, just like Lake Mead, was 95% full and appeared to be sustainable. That just happened to be right at the time when major drought took over the area, where the El Nino patterns had flipped for almost not nearly 20, almost close to 20 years, 18 years. And most importantly, it's a time where there was major increases in population as well as redistribution of population to the desert Southwest, creating a pattern that, quite frankly, I don't think anybody sees as sustainable moving forward. It was really by the end of that year, 1998 to 1999, where precipitation has fallen 70% below average. It lasted through 2017, and in fact, with the exception of that 1 year, it's still been in that really low rain pattern, which is, again, in light of climate change, is not expected to improve anytime soon. So this just gives you a perspective on the maps of water in Lake Powell. Here's 1999. You can see how sort of massively large and back up into various canyons the Lake Powell spread. As a result, there are many examples of vacation homes and ranches and things like that built not on the coastline. It's not a beach or anything like that, but near the water. By 2000, you can see notable recession of the water into what's the central core of Lake Powell. By 2002, that had increased, and by 2004, Lake Powell, many branches that had some development on them have actually completely dried up and are now dry areas. Of course, they can't be developed, nor should they be developed based upon sustainability grounds, but they can't really be developed because these could be flooded again if the rain patterns change. So this process is continuing on and on, again, adds to the water stress in the region. So putting that in here's aerial photos, putting that in an image. Here's mid 1999. Here's the 18-month change, which should give you some appreciation for just how much has changed. This area was sort of a little peninsula. This was all below water, but shallow water in the area, a bit of an island. And now this is all sub aerial, and there's just actually a river channel that flows through the lake in the area. And today this looks continues to look much more like this than the former scenario. So key things here: current drought, particularly between 2000 and 2012. The basin only produced average or above average runoff in 3 of the years. 2017, which came along later, was a big one, but effectively 9 years they were basically drawing from the reserves of water that had been accumulated in the region, and the reality is that they only met what they needed to have 3 times in 12 in the area. Lake Powell fell to about a third of capacity by 2012, which is the lowest it's seen, and it's actually I think the last I looked was a few weeks ago. It was about 40% then. Obviously, this has a great implication for minimizing the ability to use water downstream. The way the controversy it's ongoing in that area is the way the water is distributed is largely based upon the population set in 1920. So if you're living in California, particularly in Southern California, you have your allocation of water, and you can basically maintain agricultural activities in the area because your allocations can be used, brought to California, and you can keep farming and keep hydrating the soils in those areas to grow crops, and you can even generate hydroelectricity along the way. However, if you're living, for example, in Arizona, if the levels for water release go down, you're effectively left in a situation where there's lower amounts of water, and they're limited from actually doing any hydroelectric power generation in the region. So can anyone take a guess as to what the net result has been since about late 90s and 2000 in terms of the amount of hydroelectric power generation in the region? Yep, the hydroelectric power generation decreased. And if you want to think about this from a sustainability perspective or a climate change perspective, what do you think is brought in to the region to mitigate that the issue where there was no hydroelectric generation in the area? The main response has been power we can generate rapidly. So what that's become has been largely, particularly starting about 30 years ago, is fossil fuels, coal-fired power plants. Okay, so the basic premise in the 1920s about growing this area was that we would have a renewable source of power. We could populate the area. The City of Lights in Las Vegas was largely driven by hydroelectric power. Today, by the late 1990s, early 2000s, what we've seen is that the water supplies have been less secure. Hydroelectric power generation is down, and the net result is that we actually have to build more power plants, which of course release fossil fuels, use fossil fuels and release carbon dioxide in the atmosphere. So it's sort of a downward spiral once things aren't sustainable. And then by the January 2017, we talked about this major monsoon event or El Nino event in light of California water supplies. Lake Mead dropped to just about 8 feet above the level which Arizona and Nevada would have to begin water rationing and basically no longer provide water to the municipalities or all the municipalities served by that area. So water conservation in the area is great. And I knew it was about 40%. It was 39% as of a few weeks ago. Key thing here is if the levels continue to fall, Arizona and Nevada will soon see reductions in their allotment. One of the social justice concerns I want to highlight here is that these states are largely using the water for drinking water and power generation, both by hydroelectric and actually to serve fossil fuel needs, and less so for agriculture. The percentage that California gets, of course, their population's increased as well, is largely meets agriculture needs. That does have benefits to the entire country and the world in terms of food generation, but it's a realization or it's a consideration we must think about in terms of how this is allotted equitably. So there's a big push. The punchline is a big push to rethink the concept to allocate water based, reallocate water based on population. So obviously that's controversial if you're a California farmer, but as a result, there's a major questions in terms of how we can better allocate the water, more equitably allocate the water, and or what solutions we can find to make sure we can, minimize the amount of evaporation or the amount of water storage in those areas. But long term, this will be an issue that'll be a major multi-billion-dollar issue that plagues the region and eventually plagues sustainability of the communities in that region, over the long term. So there have been some experimental efforts in the last few decades. One of the things I may have not mentioned yet is that because of the allotment of water, there's actually no longer a Colorado River that discharges into the sea. It's not just the sediments that aren't getting there. There's actually no longer natural, no longer in its unnatural state we've created, Colorado River water reaching the sea. So this has been going on for, I think, the largest since about 2000. All of it's consumed in U.S. and Mexico. And in 2014, there was an experimental pulse of water released from the Morelos Dam close to the U.S.-Mexico border, where they released 130 million cubic meters of water. and this, for perspective, roughly small pulse, it was less than 1% of the Colorado River's flow at the time. And can anyone, think about what we lost, and then you can kind of consider the effects, right? We know we saw the drawdown of lakes and dams. We know we've seen the decrease in riparian zones and wetlands, and we can imagine what happens when you actually start letting water flow to this area that's been water starved for a long time. The first thing that people observe is that groundwater recharge, this managed aquifer recharge concept we alluded to, actually started to occur naturally. The rivers had drawn down, the water table had drawn down. And the result, when they started to flow the water across the river, they were losing more water than expected. That was water just percolating into the ground and resaturating the aquifers. So for starters, that has great benefits to storing water, not seeing it lost to evaporation, and has great benefits to local areas in terms of the fact that they actually have a bank of water they can access when needed. The other things, of course, is on this river riparian zones is that you see increased vegetation, increased activity of migratory birds coming in the area, and actually relatively quickly they respond to that. So this is just some images. This is a stream bed before and after the pulse. You can see here, this is a dry, riverbed. It just looks like, really poorly sorted sand. Once it was, flooded, of course, very slowly. This actually area flooded, and you can see that where this soil would have really sand would have very quickly taken up water that actually allowed water to recharge in the region. So here's just some images of August 12th, 2013, August 5th, 2014. So 1 year of difference. Notice particularly in some of the areas you see greater amounts of water sort of pooling up, but notice the increases from 1 year to the next in terms of the amount of vegetation that was growing in the area. The life has the capacity that particularly plants have the capacity to respond quickly when the water becomes available in the region. So where I want to close there really is that thinking about the Colorado River, it's a major source of water, sustains life in the region, has an incredible economic importance, and nonetheless, it is probably one of the biggest sustainability issues facing American and Mexican society right now. The area, again, basically is responsible, even though it's a relatively small river, 3% of Mississippi River, hydrates and creates water for power, food, and life for more than a third of the U.S. population, and plays a really important role in doing so. So what this is going to kick off, and we'll transition into now, is basically a broader discussion of water resources in the U.S. and actually internationally as well. So we've talked about rivers and floods and how much damage that can do. We've talked about drought and how water shortages can impact society and some of the factors that lead to drought. But now we need to just talk more directly about how we're going to actually obtain and utilize water. And this is, again, as I highlighted in the drought discussion, is one of the greatest issues facing society, right? Water poverty, literally having too little water. That's the terminology used for water poverty, and the definition of water poverty. And access, or insecure access to water, again, plagues between 2 and 3 billion people on planet Earth. Almost a third to 40% of the population of our planet doesn't know, securely where their water is going to come from the day to day, or is left waiting for, bottled water or something to be delivered because of the fact there's no secure water in our region. So briefly, what I'll do here is talk just a bit about what water is. I think hopefully all these things are just review, but it's sort of part of our STEM folks, make sure we cover some of the basic science regarding these things. Water, again, is a compound that has no taste or smell. That's if that's not true for your water, you probably have a problem. Generally, water is benign, but of course there are certain instances where it can be quite dangerous and where it can scald or freeze you. Obviously, as we talked about in the last few weeks here, is that when there's too much, it can strike and destroy land and life. When there's too little, the devastation might not be as quick, but it's quite profound. Obviously, I think we learned this, and hopefully you all learned this in elementary school. But water is everywhere. Most of all biological life depends on it. Things like humans are 65% water. Animals like cows, particularly with higher fat content, are up to 75% water. Most vegetables are a high percentage of water as well, up to 95% tomatoes. Importantly, this is one of the main things about water that's still poorly understood from a chemistry, pure chemistry perspective. It actually behaves quite differently than similar compounds. In general, you can predict the behavior of most compounds based upon similar aspects of the periodic table. In the case of hydrogen selenide or hydrogen sulfide, they're actually can be quite toxic, whereas water is, of course, greatly beneficial. Of course, we all hopefully have heard this before. Hopefully, mainly it's a review, but there are some key properties of water we're going to review here nonetheless. Or that most liquids, actually contract when chilled. Remember, water will contract till about 4 degrees, but as it gets closer to freezing, it starts to expand again. This obviously has major implications for things like lakes and whatnot, not freezing over entirely. The ocean's not freezing over entirely. But as a result of the fact that from 4 degrees Celsius to 0 degrees Celsius, and don't worry, I won't test you on those numbers, although it's probably useful to keep some of them in mind at least. Is that when frozen solid, there's about a 10% expansion or about 10% more volume to the water, which causes it to expand. If you ever mistakenly put a beer can or a glass bottle of water in a freezer and forget, chill it down rapidly and forget, you've probably learned that lesson the hard way. And as a result, as we all know, when water's frozen, because of the expansion, it becomes less dense and actually floats, which is sort of a unique property of water as far as we know. Very few things, almost, I don't think there's anything we know that behaves like that in nature. Obviously, we won't stress this because I think most of this is a review. That makes water essential for life and the development of life on Earth, and obviously our continued existence. Nonetheless, as we've alluded to, we have relatively poor control over it, both in terms of floods or droughts, and actually one of the main focuses we're going to talk about for the next week or so here is how we're going to consider it as a resource so that we can make sure we have an adequate amount of it in normal times, just to sustain life, sustain food development, and other components. And a lot of that we'll be talking about just recognizing how we use it and really getting a handle on the immense volumes of it that we do use. So, I think I mentioned this already, but if ice didn't float, obviously we see no life. Most of lakes and rivers would be frozen solid, and we wouldn't see any existence there. So, getting into the actual nuts and bolts of water, where's the water? I think all of us, at this point in time, probably recognize that the oceans make up the vast majority of water on Earth. The oceans make up nominally 75% of the Earth's surface, and importantly, the oceans make up 97.2% of the water on Earth, or at least the water on the surface of the Earth, I should say. You might have heard in popular press, or if you're a science nerd, maybe you read this in science literature, but there is a statement. There's some research that suggests there are about 3 to 4 volumes of the global oceans we see on the surface of the Earth, which again make up about 1.2 billion cubic kilometers of water. There's an argument there's about 3 or 4 times the volume of water in the Earth's mantle and in subducting plates. Obviously, we're not really talking about that here. There's a few reasons for that. One is that it's not well constrained. There's still a lot of debate whether it's 2 or 5 or whatever the case may be. But the other aspect, of course, is that we can't really access that water at all to use it for drinking water, for irrigation or power generation, directly at least. There's some locations where, of course, we use it for geothermal energy when we can access that where possible. So obviously the punchline here is that 97.2% of all the water on the surface of the Earth is accessible to humans, occurs in oceans. The nice thing is that water has a residence time there of relatively long time, so a few thousand years. That doesn't mean the oceans have only been there a few thousand years. It means that water evaporates, moves on to continents, and goes through the hydrologic cycle that we have alluded to, and I'll bring up here certain components in a minute. But the key here is that these are obviously big reservoirs of water are basically unusable to us for drinking water, for irrigation, and actually for most cases even for power generation. So the reason that, of course, is the salinity. There are major efforts recognizing the immenseness of the ocean volumes of water that we could maybe try to do desalination and things like that. And there are major scientific efforts ongoing to desalinate water that have been ongoing for, literally, decades at this point. So the key thing here is most of the water is in the oceans. Nonetheless, that water is almost unusable for us for water supplies, be it, human consumption, um, sanitation and hygiene for washing or flushing toilets and whatnot, um, or for power or electric generation, or power electric generation and or agriculture. Obviously, I think the agriculture part makes sense to most people, as does the human consumption. We can't drink salt water; our bodies can't do that. It actually leads to dehydration, kills plants. In fact, you hear the term salting the earth. Salinity will actually cause the plants osmosis to push the water out and kills plants. A little bit hard to understand why it can't be used for power generation, but basically comes with a corrosion argument where water can't be used around a lot of metals. Salt water can't be used around a lot of metals. It causes the metals to corrode. So what this sets up for us, and what we're going to continue to talk about later in this week, is that these bottom sources, the atmosphere, rivers, streams, groundwater, lakes, and ice caps, including ice caps and glaciers, make up the vast majority, almost all of the rest of the water, and are really the only considerations we have for water that we can access for drinking water, agriculture, or power generation, or water, sanitation, and hygiene. I'll start at the bottom of this list. Sort of similar to oceans, the next biggest slug of water, in fact, 2.1%. So that leaves basically, that means that 99.35% of the water, so less all but 0.65% of the water is encapsulated in either the oceans or in ice caps and glaciers. Clearly, you all recognize in light of climate change, where glaciers are melting, and in many cases, even where just the annual snowpack melt, just like California, there are many populations that actually rely on ice caps and glaciers for freshwater supplies. But by and large, we have to recognize that these are thought to be stable for tens of thousands, up to millions of years. And as a result, ice caps, except for small amounts that melt off by sublimation and whatnot, are actually not also not part of the freshwater cycle that we can use in most locations. This has clearly changed a lot in areas where the snowpack melt, or this is, caveat being this is different in places where the snowpack melt, California, India, Bangladesh, Pakistan, where there's melt from the Himalayas are exceptions. And then a lot of the populations that live along the Andes have developed almost exclusively glacial meltwater usage for fresh water. But most of the rest of the water used for drinking water or other industrial purposes come from lakes, groundwater, rivers, and some direct capture from the atmosphere. So in our part of the world here in Ohio, I don't think it won't be any surprise to anyone. Significant volumes of lake water are used, particularly north of us, in areas like Cleveland, Detroit, major industrial hubs of the last century, Buffalo, New York, Erie, Pennsylvania. A lot of them depended upon, really abundant access to fresh water. And, in the United States, particularly in the Great Lakes region, we are blessed with the largest freshwater supplies in the world. Importantly, these lakes have relatively small amounts of residence time, and as a result, they need to be treated very carefully in terms of a sustainability argument for how the water is managed, because small perturbations to the water cycle can have pretty profound effects to water access. Most of the water that's actually going to be used for rivers, for drinking water, irrigation and sanitation, and other industrial activities like power generation, come from rivers and streams, even though they're actually much smaller in volume than groundwater. And actually, as you notably can see in areas that have flood and whatnot, have very short residence time and change continuously. In central Ohio, places like Columbus, for example, Dayton, depend almost entirely on rivers and streams. Our reservoirs up to the north part of the city, and in Westerville and Dublin and totally drawing a blank on the name of the other town there, all are related to rivers that are basically been dammed up. Reservoirs been put in, dams been put in to sort of catch the water and create a resource that we can turn on to the pipeline infrastructure for the city of Columbus. Areas in this part of the world, that's a pretty common phenomenon. Same for Dayton, same for Cincinnati. Rivers and streams, even their small volume, actually make up an important resource of water for most locations. If you follow the Mississippi down, many of the cities along the Mississippi River, Ohio River, etc., are all using rivers and streams. In comparison, even though groundwater is significantly larger than the other resources, makes up the third biggest component of the water. It's actually used less often for drinking water, irrigation, and other industrial activities than most other water resources. The biggest reason that groundwater isn't used to the same extent is sort of multifold. One of the bigger reasons, of course, is simply economics, right? Economics typically drive a lot of decisions, and as a result, it takes more energy and more cost to drill a well, and more energy and cost to pull the water out of the, pump the water out of the well. And as a result, even though it's often a much more abundant source of water than rivers, it's not used as commonly, particularly in areas like the U.S. Obviously, as we've alluded to in terms of California, the High Plains Aquifer, each of which we'll talk about more in this, as we go on later this week. It's really important water resource in many areas, but by and large, many American industrial cities, were basically founded because of their access to either lakes or to flowing river systems. Particularly in the last 2 centuries, industry really liked the idea of rivers because it carried pollution and waste away. And as a result, rivers and streams are often a really important component of water, of the water supply, disproportionately important component of the water supply relative to the percentage of water that they made up. The last component we haven't talked about, as I've jumped around through this list of water sources, is the atmosphere. By and large, up until probably this decade, there wasn't any real serious consideration for the role of the amount of water in the atmosphere other than it causing storms or droughts, how it affected weather patterns and climate. But today, as we'll talk about, probably early next week, there is a growing interest in actually trying to look at direct capture of water from air to create water supplies, particularly drinking water supplies. From a mass volume perspective, it's basically almost 10 times larger than the amount of water in rivers and streams, which is heavily utilized for water supplies around the U.S. I've already shown you this image. I won't go through this in any great detail again, other than to remind you that the sun is what drives the hydrologic cycle and ultimately dictates where the water is relevant to these water resources. Clearly, it changes the amount of water in the air on a constant basis, and leads to water being deposited for surface runoffs of rivers as well as groundwater and the other factors. So we have to give proper homage to the sun as the ultimate driver of this. But we're going to spend most of the next probably close to a week, at least the rest of this week and early next week on, is kind of going through the key aspects of how surface and groundwater are, what the characteristics are, where we find those water resources, and how those water resources are utilized, particularly in the U.S. We'll use a lot of examples, but also around the world in terms of meeting our needs for various purposes. So what I'm going to do, rather than start up a new topic right now, I'm going to end there. We'll pick up on water resources for our lecture on Friday. And just a reminder, there's the last worksheet is due on Friday night, and a new one will be posted on Sunday. So I hope everybody is having a great week, and we'll pick up with water resources on Friday.